I will begin. Heavenly Father, we thank you for this day, and I just pray that you'd help us to glorify you what we do, so we'd learn a little bit more about series and how to analyze their convergence and divergence, just to give the students discernment to understand the difference between the ideas here, Lord. In your name I pray. Amen. All right, so a couple more tests to get out of our system here. Limit comparison test. Limit comparison test, aka the LCT. I talked to you guys about the so-called direct comparison test before, which is just what it sounds like. Limit comparison test is for series with positive terms. So we have if a sub n and b sub n are greater than 0, all right, so assuming positive terms, and the limit as n goes to infinity of a sub n over b sub n is equal to L, all right, which is where L is finite and positive, so I can say that is an element of 0 to infinity. Let me put it in words. L finite and positive. All right. So if the limit is L, where L is finite and positive, then the series with term an and bn either both converge or both diverge. Both converge or both diverge. In other words, they're both summable or they're both not summable, right? He gives us a proof of this. Let's see if we can follow it. So he suppose that the limit as n goes to infinity of a sub n over b sub n is equal to L, right? What's that mean? That means that there exists some, let's say m, in the natural numbers, right, such that n greater than m implies what? What does it mean for the limit to go to L?
So what does it mean for the limit to go to L?
Yeah. He's kind of most mysterious inequality here. It's bothering me. Well, I mean, directly it would mean that we can choose, if we go far enough out, right, then the difference an over bn, right, minus L is what?
Should be some small epsilon, or very close to 0.
Right, is as small as we like, right? As we desire, right? I mean, we usually call that epsilon, right? So I suppose what he does is he picks m for epsilon for epsilon equals 1 to be achieved, right? So if you can pick an m such for epsilon equal to 1, that gives us that the an over bn minus L is less than 1, right? So if I pick the m that causes this for, for n greater than m, then can we unwrap that inequality? What does it mean to have an absolute value inequality like this? This means minus 1 is less than an over bn minus L is less than 1, right? Which isn't terribly surprising. The left-hand side of this inequality is not terribly surprising. That is, in other words, 0 is less than an over bn, right, is less than L plus, oh, I'm sorry. Goodness gracious, my bad. Add L to this inequality, we get L minus 1, right? L minus 1 is less than an over bn is less than L plus 1. So let's see here. Once you have, and this is, of course, again, for the n greater than that m, which causes the terms to be within 1 unit of L. Let's see here. Now, these terms are positive, right? So this, let me call this inequality star. There are two things we could do with this, right? Multiply by bn, what do we get? L bn, well, I'm sorry. L minus 1 bn, right, is less than an is less than L plus 1 times bn, right? So what good does that do? Well, let's suppose that the sum over an converges, right? Then you can see from this. Now, I guess does he assume that L? Well, I mean, I guess, well, fine. I mean, oh, yeah, this doesn't quite work. This actually will not do it. He actually mentions we need to look at flip. If this is to get the one I'm trying to do right now, we actually need to look at 1 over L instead of L. So like the proof for the one I'm trying to do right now doesn't actually come from this. If we flip this limit as bn over an, you get 1 over L. And so that will give us a related inequality. Let me behave here. So suppose this diverges. If this diverges, then what? If this diverges, then the sum over L plus 1 bn, right, is 0. I mean, an is a term with an and L plus 1 bn. These are both positive term series, right? And if this diverges and this one has larger terms beyond some point, right, the tail of it, then this diverges by what? Right, by the direct comparison test. Sorry, let me just briefly go through the other one. The other direction would be something like this. We have the limit as n goes to infinity of bn over an is equal to 1 over L. If L is positive, right, if the limit of the one quotient is L, the limit, the reversed, the flipped quotient is 1 over L. That makes sense because L is positive, it exists. And so this means that you can pick m such that m greater than, n greater than or equal to m implies that the absolute value of Bn over An minus 1 over L is less than 1, right? Which is to say that Bn over An minus 1 over L is less than 1 and greater than what? Minus 1. And then if we add 1 over L across the board, what we got? 1 over L minus 1 less than Bn over An less than 1 plus 1 over L. Let's see here. Then multiply by An, what do we get? Right? That's the estimate that I need to get the direct comparison test in the other direction, right? So if you look at this, if the sum over An converges, then the sum over 1 plus 1 over L times An converges, right? Which implies that the sum over Bn converges by a direct comparison test. This he doesn't have. This he just says you can do in the book. He doesn't actually give you the details of. I thought it'd be healthy for us to actually prove something in here on occasion. So this isn't too bad. It's worth kind of just looking at. So all these tests, they're not dark magic. They can be proved through arguments which are not much more sophisticated than what we do in here in terms of the problem solving. But of course, your primary responsibility in here is problem solving. I don't try to hide that. Okay, so let's look at some nice examples. He's got a nice example. He's like the sum. This is very greedy. 1 over An plus B n equals 1 to infinity. I'm going to assume A is greater than 0 just so I don't have to worry about, like, if A was minus 1, you know, if A was minus 1 and B was, you know, then we could have division by 0. That wouldn't be good. And you know what? I'm just going to go ahead and assume that B is greater than it could be 0 even, but greater than or equal to 0. And if I do that, that way we have a positive term, right? Then I can look at this thing as being, say, A sub n is greater than 0. A sub n equals to 1 over. Let me change that to a big A, so there's just no danger of confusion. Okay. And I'll change that to a big B so we don't get confused. So An plus big B. There we go. And I'm assuming that these are constants, A and B greater than 0. All right. Of course, you could try a direct comparison test, but limit comparison test is easier to think through. I mean, because you notice what you don't need to apply limit comparison test? What don't you need to apply limit comparison test? What's the thing you guys are really bad at? Me too. Honestly.
Coming up with another function that mirrors that one.
Yeah, well, that's right. Coming up with another function which is related, but correlating to that, coming up with these things, right? Inequalities. Inequalities are tough. Where's the inequalities in limit comparison? There's these. Those are harmless, though, right? So the question is, what do you want to compare it to, right? Oh, come on. What? How dare you? Man, I have not made it yet this semester. All right, so I think we should compare to, what do you guys think? What is this like? Yeah, just.
Sorry, just 1 over constant A.
It's like, yeah, like 1 over an. How about how about the p equals 1 series, right? I mean, compared to p equals 1. So, in other words, the sum n equals 1 to infinity of 1 over n, right? So here my bn will be 1 over n. Let's make sure we have the right to do it. Is it positive? Yup. Is this positive? Yup. So I can apply the limit comparison test. Limit n goes to infinity of 1 over an plus b divided by 1 over n, which, let's write this like civilized human beings. This is the limit as n goes to infinity of n over an plus b. How do you guys want to do this? We could do L'Hopital's rule. We could do algebra. I'm going to do algebra. How about that? Algebra says, hey, divide the top and the bottom by n. Right? What happens as n goes to infinity? B over n goes to? Where does that go? Right, that goes to 0. And so we get 1 over a, right? Which is positive, right? Finite. Thus, by the limit comparison test to p equals 1 series, we find the sum n equals 1 to infinity of 1 over an plus b diverges, because it shares the same fate as the harmonic series by the limit comparison. I mean, this is what the limit comparison test tells me. They both converge or they both diverge. Yeah.
Like on the test, do we have to say like by what theorem?
On the test, you have to explain what you're doing. Yes.
Like,
Yes, you do.
how you said by the limit comparison test.
Right.
We have to know that and say
Yeah.
by that.
Yeah. I do give partial credit, you know. So if you're like, by that convergence test that involves a limit, I'm probably still going to give you full credit. But, you know, we call it the limit comparison test. That's its name. And then because we hate actually writing that out, it's the LCT, right? And because I can't stand actually writing out direct comparison test, I write DCT. And, you know, so.
So abbreviations are fine as long as you know what they mean.
Yes, abbreviations are fine as long as they're sort of ones that have come up before in lecture. Don't be like my wife. Don't just make up abbreviations. Like when I met my wife, she started talking about DC this, DC that. I'm like, what's DC? Digital camera. Like, this is not an abbreviation that people use. But apparently, her and her circle of friends, they just abbreviate common everyday household items. I guess it was preparing her to work here. But because this place is awash in abbreviations, isn't it? DCP, LUO. What are the other ones? The ROT. Oh yeah, let's not forget about that. Maybe we should though. I don't know. Oh, here's one that's got a little bit more sting to it. This is example 5. He's got the sum n equals 1 to infinity of n times 2 to the n over 4n cubed plus 1. I'll come back to this one in just a second, but you know, this first example, I should call this example 2, huh? This is actually his example 5. Section 9 point, where are we? 9.4, although we've been around. This is example, guess this is example 1 of section 9.4. It's got a few others. Let me just say in words, though, rather than doing a bunch of writing, you guys. If we have something like, I'll get back to this one in a second here. I'll just put it up there. But more generally speaking, if you got something like 1 over n to the p plus stuff, right? If you got 1 over n to the p plus stuff, such that 1 over n to the p plus stuff is greater than 0, right? Then sort of morally, intuitively, however you want to think of it, this is essentially the p series. So whatever the rest of that stuff is, supposing the stuff is like lower than order p, all right? So I mean, like maybe it's n cubed plus n squared minus 17n plus 347, whatever. The point is, the only thing that really matters is the n cubed. After a while, it's just like the n cubed series. And the limit comparison test basically proves that, because if you take something like this and you compare it to the p series, you're going to get a limit which is 1. Because the n to the p terms dominate when you do the limit comparison. So essentially, one of the things the limit comparison test says is essentially you can sort of focus on the highest order term in the ratios, like intuitively. We should still actually check with the limit comparison test that's actually how it turns out, but this is kind of an intuition where you should go. Just to be more specific, guys, if I have something like this, 1 over n to the 17th plus n squared plus 2, I can tell you that this is going to be convergent by limit comparison test to p equals 17 series. Because if you work out the limit of that versus, if you do 1 over n to the 17th plus n squared plus 2 divided by 1 over n to the 17, well, that's equal to n to the 17th divided by n to the 17th plus n squared plus 2, and that goes to 1 as n goes to infinity. So by the limit comparison test, they share the same fate. P equals 17 series converges, right? By the same token, if you, well, anyway, there's anything kind of like that. There's other good examples in the section. How about this one? I don't know. This one kind of scares me just looking at it. I don't know what to do. Oh. He says it's pretty clear to compare this against, and do you see his logic? So this is essentially n 2 to the n over 4n cubed. Ignore the 4, right? So that's essentially 2 to the n over n squared.
How did he do that?
Well, if you think about n going to infinity, right, the 1 is irrelevant. The 4 is just a factor, whatever. So this is really like n times 2 to the n over n cubed, right? Which is really like 2 to the n over n squared. And then if you start thinking about it, nth term test, you notice that the sum n equals 1 to infinity of 2 to the n over n squared diverges by nth term test, right? Because if you calculate the limit as n goes to infinity of 2 to the n over n squared, what do we get by L'Hopital? If you'll allow me this notation, I'll allow you this notation. Sound good? So by the double L'Hopital, extending n continuously. So much legalism to take care of here. Natural log squared 2 to the n divided by 2 times 1, right? Which is infinity, yeah. Which, of course, is not equal to 0. Right, so here I'm... And what kind of limit are we doing? Looks like infinity over infinity, right? Both times. So that diverges. So that's a great, and that's like the limit we're given. I mean, like the series we're given, so we should use limit comparison on this. So we calculate the limit as n goes to infinity of n times 2 to the n divided by 4n cubed plus 1, all divided by 2 to the n over n squared. So we got to do algebra. Where's algebra take us? It takes us to n cubed times 2 to the n divided by 2 to the n times 4n cubed plus 1. The 2 to the n's cancel. We got the limit as n goes to infinity of n cubed divided by 4n cubed plus 1. Right? What's this limit equal to? Do I need to write down more work, or can you see it? I guess I'll write down more work. Limit as n goes to infinity. I mean, I'm okay with you guys writing the answers to these sorts of things down by just looking at it. It's sufficiently close to the answer. I'm not bothered too much if you don't show me this next step, but it's better if you do. So this goes to 0. And so the answer we get is 1/4, right? Which, of course, is positive, right? Thus, S diverges by limit comparison test to the sum 2 to the n over n squared. And I just invented a label because I'm tired of writing that. You can do the same. I would like you to be precise, though. So I get really annoyed if students say it diverges by limit comparison to that. I want you to tell me what's diverging. So, I mean, just there's a simple thing to do. Just call the thing you're trying to analyze S, and you can refer to it. Yeah? And then I know what you're talking about. If you just say it diverges, and you've got like more than one series floating around, I don't know which one you're talking about. And there are problems where there's like 2 or 3 or 4 series kind of floating about, and I don't know which one you're talking about unless you make it clear. So it's just a good habit and to try to be precise, you know. Any questions? Yeah.
How did, when you use double L'Hopital's rule, how did you get exponential 2 squared?
So when I differentiate 2 to the x, I get log 2 times 2 to the x. So if I do two applications of L'Hopital's rule, each differentiation pulls down a log 2. Yeah. Yep. All right, so this limit comparison test, it'll take down a host of problems. There's tons of problems that are pretty difficult to do with direct comparison that with limit comparison are like relatively easy. It's a pretty significant tool to know about and to use. It's very useful. Of course, if something is, you know, telescoping or geometric, it's probably not the right tool, but it's a useful and important tool. This brings us to section 9.5, which is on, oh, by the way, Joshua, we were talking about a problem earlier. You just keep doing what you're doing to start with. Like you got to,
Before I started using L'Hopital's rule of times.
you were on the right path. I should have just told you. I should have just told you the L'Hopital again. This is the limit. We're talking about the what is it? Cosine of pi over cosine of pi over 2 minus x to the x power.
Yeah.
9.4?
Did I write 9.4? Oh no.
I wish.
So,
Okay, that-
so this problem in your homework, the cosine pi over 2 minus x to the x power, it's the usual thing. You want to rewrite x as 1 over x in the denominator, and then like clean it up, apply L'Hopital's rule again, it works out. There is another lazier way to do this problem though, Josh. So this problem we're talking about, I shouldn't really tell any of you guys this, because now that I told you this, you're just going to do it this way. But what is this equal to? No, not 0. Can you guys, what is that, if you use the adding angles formula for cosine, what is it? Cosine of a plus b is what? Cos a, cos b, minus sine a, sine b. What happens if you apply that? What is this mysterious cosine pi over 2 minus x function? This is, well, here, let's make it prettier. This is cosine of x minus pi over 2. Let me just clean it up. Right, cosine's even. So this is cos x, cos pi over 2, minus sine x, sine of minus pi over 2, also known as sine of x. So this is really sine x to the x, which we had an example in class that proved that goes to 1 as x goes to 0 from the right. So it is a sneaky recasting of a class example. That is the lazier solution to this problem. What you were trying to do is the right way to do, which should gain you experience, which you need. Because on a test, are you guys going to see this? No, you're not going to, because none of you knew what I was talking about 3 minutes ago, right? None of you look at that and go, oh, that's sine. Now, you should, right? You should have been taught trigonometry well enough that that is second nature to you, but it's just not the case, right? To borrow the terminology of Dr. Sprano, you were cheated, right? Your previous math teachers cheated you. So we try not to cheat you, but sometimes it feels hurtful. Let's see here. But yeah, the intended solution there is what you were doing, Josh, which is convert it to use the indeterminate power method, and then you apply the L'Hopital's rule to the thing inside the exponent and so forth. All right, section 9.5 is on what are called alternating series. Alternating series are I don't know, the only thing I can think of that I'd say is more fun to work with is a geometric series. Like, alternating series have such nice properties, and here's what they look like. So a series is said to be alternating if you have, it's of the form something like b, say b naught minus b1 plus b2 minus b3 plus dot 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 dot, where b sub j are greater than 0 for all j. In other words, an alternating series has the following formula. It's something like the sum j equals 0 to infinity of minus 1 to the j bj. So this is an alternating series. The alternating series test is really quite beautiful. Here's the theorem. It's beautiful because it's simple. And, oh man, come on. Well, I refuse to write it the way he did. The alternating series. The reason I'm using B here is there's a good reason for that. I mean, it's because we've been using A and for the sort of arbitrary element of the series. And he's using, I'm just not even talking about it, n equals 1 n equals 1 to infinity. Oh, so, grief. All right, fine. So he's like this, or this. So what he's getting at here, guys, is just that his alternating series could either start with a plus, right, or it could start with a minus. Great. It can either go minus plus, minus plus, minus plus, or it could go plus minus, plus minus, plus minus. But either way, we're going to say it's alternating. Fair enough. I like that. Converges when the following two criteria are met. Number one, we need that the limit as n goes to infinity of b sub n is equal to 0. 2, we need that b sub n plus 1 is less than or equal to bn for n much greater than 1. Eventually, we need that the terms are decreasing. Okay. He says for all n, but in my heart, I know that we should just say that this condition is met eventually. Yeah. Oh, by this I mean for n sufficiently large. I'm giving you a greedier theorem than actually in your book. Your book says for all n. I say that you can be a little bit more freewheeling than that. It's okay if the terms are not decreasing right away, as long as they're decreasing eventually. You can pick off the first finite number of terms, separate that off as a finite number, and then just deal with the series beyond that point. And you can apply his alternating series test to that. Basically what this, when I was in grad school, I had a fellow grad student who used to call this the wishful thinking test. Because most of what it essentially says is that when the nth term test works, it converges. But it's not quite honest. You also need decreasing terms. Okay. In principle, you could have, I suppose in principle you could have the, how could you have that? How could you have the terms not, I'll shut up. Shut up. I don't have enough time to go chase rabbits at the moment. I must give you an example. So here's the quintessential example. This is the so-called alternating harmonic series. And this one is the sum n equals 1 to infinity of minus 1 to the n plus 1 over n. All right. So put in n equals to 1, what do you get? You get 1. Put in n equals to 2, you get minus a half. Put in n equals to 3, you get plus a third. By the way, there is a proof of the alternating series test in the book. I probably should go over it with you, but I kind of think that it's more important for me to work problems for you guys than me to work out the proofs. You can read the book and the proof in the book, and I'm happy to talk to you guys about it. If you want to see proofs of everything in here, if you go back a couple of years, about 2 years ago I proved everything, and I got the worst course evaluations ever for some reason. But I don't know why that is. Apparently students do not like it if you prove everything. Weird. True though. This is the alternating harmonic series. Look, you can draw a picture of it. And the picture is very insightful. So here's 1, right? Which is, by the way, S1. What's the second partial sum? S2 is here, right? It's 1 minus a half, which is otherwise known as a half, right? And then what do? You add a third. So that takes you over to here like that, right? This is S3. And then you subtract a quarter, which puts you here, right? And then you add a fifth, right? Add a fifth. Subtract a sixth. Add a seventh. Subtract an eighth. Add a ninth. Subtract a tenth. Add an 11th. Subtract it. You get the idea. And so apparently, we're zooming into, it converges to this, right? Whatever that is. From my picture, you can see that that's the natural log of 2. Right? I mean, it's fairly obvious that this converges to about 0.692 something or other. I'm being facetious, of course. This is not at all obvious. No, it's not obvious. It's not at all obvious. But there is this amazing theorem which says that the sum, let's say j equals 1 to n of minus 1 to the j bj, right? Oh, here j equals 0, 0 to n. That this minus, the thing that it converges to, so like so this is the nth partial sum, right? Minus the actual series. So this is what you'd call the error, right? In Sn, it's how far it is from the truth. And so if you look at the picture, you can even see it here. Wherever you are, you're always within the next thing you're adding or subtracting within the answer. So the alternating series estimation theorem is that this is less than or equal to b sub n plus 1. That's pretty nice. So like, for example, S3, which we figured out was 5, what's a half plus a third? 5/6 is within B4, which is equal to 1/4 of the answer of the sum of the series. I'll just write it. I should have given this thing a label. Why didn't I call this thing S? I should have called it S. It's too late. Oh well. That's the alternating series estimation theorem. So if you want to calculate an alternating series to arbitrary accuracy, all you got to do is look at the positive part of the nth term and make sure it's sufficiently small, and then good to go. This is pretty nice because it turns out that the power series for the sine function and the cosine function, these are alternating series. So this actually we can apply later to sines and cosines to make sine or cosine as accurate as we like to a given value by just adding together a finite sum of terms. We use this theorem later. The alternating series, this is the alternating series estimation theorem, which we could prove. Probably should. I probably won't. By the way, why do I get that alternating harmonic series converges? What does it meet the conditions of the test? Let's see here. We got Bn is 1 over n, right? So 1 over n plus 1 is less than or equal to 1 over n. Therefore, Bn plus 1 is less than or equal to Bn. So in other words, definitely decreasing, right? Decreasing Bn, like we need. That's number 2. Number 1, of course, the limit as n goes to infinity of 1 over n is what? So therefore, by alternating series test, the sum n equals 1 to infinity of minus 1 to the n plus 1 over n converges. proving that it converges to log 2 is something we'll actually find a technique to do that. But we're not quite there yet. That's just kind of like the pi squared over 6. It's just mystical information dropped upon you for no particular reason other than shock value. And or saying something besides, it converges, it diverges, it converges. I get sick of it after a while. I know. But it takes a while because we have so many toys to play with. There are still 2 more that you need to learn. And we should do a few more alternating series probably. We need to talk about what's an absolutely convergent versus conditionally convergent series. And then section 9.6 is ratio and root tests, always popular. And I think that's about it for the convergence divergence stuff. There is a if some of you are wondering, like, big picture, if you're impatient and you want to know the whole story before the end, page 632, there is this wonderful table of all of our methods. So this is like some grand glorious board game where you're learning secret moves of different players. Eventually you get all of them in hand. That's page 632. Oh, and we're out of time, so I'll see you tomorrow. We still have class tomorrow, right?